Hello, everyone. My name is Caitlin Croft. I'm really happy to see you all here today for today's InfluxDB IOx Tech Talks. The entire IOx engineering team is here. So they'll be giving an update on what they're working on, and then there'll also just be lots of time for Q&A. Once again, the session is being recorded and will be made available later on YouTube. All right, Marco, I'm going to hand it off to you.
Thank you, Caitlin. So hi, I'm Marco, and I am one of the two Marcos in the team, by the way, the one with the K in it. So, okay, so today I would like to share a little bit of my experience with performance analysis with Rust. Disclaimer, I'm not really a Rust expert. I'm still learning Rust over the past 6 months. So some of those things are obvious for people, but I think it still perhaps might be useful to share this kind of perspective to how to learn to figure out what your program is doing. So there are a couple of things. I have more experience with Go than with Rust, and so some of the things I kind of gave for granted to be there as tools are not there. We're getting there, so this is a little bit of an angle I will be taking here. So, but as I said, I have no idea what I'm doing, right? So, I have some help though from some local colleagues here in my co-working space. Okay, so when you're doing performance analysis, you generally have two kinds of questions you ask, right? So one is, where did my CPU go? What parts of the program are consuming CPU, are sitting on the CPU for most of the time? The other part is, which part of the program are consuming memory, or are causing allocations, or are holding the memory for a long time? Those are two different things, although they overlap a little bit. In particular, if you're having a program who is making a lot of allocations, well, they show in the CPU profile as well, because allocating memory is a library call that does things, and so one of the reasons why you want to minimize that is because it takes time, right? And also, if you're slow at doing things, also the memory usage can blow up, because if you're, for example, if you're having many concurrent requests, and some of them are slow, they will just hold the memory they are using for doing their job for a longer time. So overall, you will be using more memory. But this is different. I would like to kind of show you the tools to see these things, and not blab about what you should do with that knowledge. Right? So the first thing, let's focus on a very, very stupid program, right? Just a bunch of threads running a short function and a longer function. So we have a function called quick, which should be slightly faster than a function that is called slow. There's a great tool for Rust, which is called Rust cargo flame graph. You just install like this, and you can just run cargo flame graph. And I guess I run a Mac, so this is a little bit of a problem. Okay, I'm a little bit too lazy to actually reboot and enable this advanced feature of the Mac, so I would just run in Docker, right? So I will run in Docker, which is a Linux thing, right? So I run in Docker, and I did install perf, which is a requirement of this thing, but it turns out that if you run things in Docker, well, the kernel is in a virtual machine. It might not be the same kernel of the image that you're running in your Docker image, so that doesn't work anyway. Okay, so let's find the right library of the right version matching your kernel, and you finally get something. That's nice. So we have a glimpse at what your program is doing, right? As you can see, there are recursive calls. There is the quick function over there in the bottom that is shorter. There's It's taking less time. The slow function is being sampled more often. Okay, so this is how you read this flame graphs. There are books written about it. I'm not going to go deeper. So this is a great tool. Now, however, if you run cargo flame graph, it's great when you're developing. You can run your benchmarks, you can run your tests under it, you can just run your stuff. And then when it's done, it will collect all the samples, render a flame graph, doing all this kind of stuff. But what if you have already a program running somewhere? So you can do the very same thing that cargo flame graph does, which is run perf or the equivalent dtrace for FreeBSD, Max, and so on, which is basically just at random intervals, well, at some cadence, it will just peek in what your program is doing, what each thread is doing. This 997 is the frequency at which this sampling is done. And it will just capture this thing into a file, and then you post-process this file and you render the flame graph. So, oops, it doesn't work. It doesn't work. I'm pretending this is a live demo. Obviously it's not. Why doesn't it work? Because, okay, small digression. This is something interesting I learned recently. So back in the days, I remember there were these things called frame pointers, right? So when you compile things, unless you explicitly ask to not have them, every function prolog will kind of save the frame pointer to the stack and get the new stack frame, position in the frame pointer, and so on. So basically, the stack will be an explicit linked list of stack frames. That makes it easy for you to compute backtraces. So you can know whenever you kind of pause a function in a given moment, by inspecting that register, you just know all the previous functions that were called. But it turns out that on 64-bit Intel, they just decided that this is no longer a suggested approach. And in fact, GCC omits them since version 4.6, and Rust seems to omit them also if you're building the binary in debug mode. So how does it work? How do you get stack traces? Because you do get stack traces when you have panic or this kind of stuff. So it turns out that the very same debug symbols, the dwarf symbols used for debugging programs, knowing how it maps to source lines, is also used to kind of know the shape of the stack frames, like how big it is, how each single instruction, if it kind of wiggles a little bit with the stack pointers and this kind of stuff. So by using this information and having just a dump of the stack, you can literally recover the same thing, but you have to include it. So it's important to include when you're building, even in release mode. If you don't want the full debug symbols, you can at least say debug one, which means just the subset of dwarf info that is needed for backtraces. So, and then you have to tell perf to use this. So this is why it's called graph dwarf. Basically is required. So now you can get the same stack trace even of a running process, which is useful, right? So sometimes you want to know how a real production server is behaving. So you just wonder why things are slow, or is there a hotspot that only happens when you have real data in it and so on. But you don't want to run the whole execution under tracing, sampling. So you can just attach to it. If you can zoom this flame graph, and there's this interesting thing. There are a few functions there that account for some time that are we just don't know what their symbol is. So who knows? Perhaps there's something interesting. Okay, so there are a few questions. So what if I want to run this thing on Kubernetes, for example, where I don't really control what the kernel version there runs? I don't want to bake a new image with the right version of perf, and then have to coordinate with my SRE every time they roll out a new version of Kubernetes and so on. What if I just want to run it on my Mac? What if I don't have a shell on prod? which I probably don't, right? So there is something, there are basic things I would like to have, and I kind of am spoiled because I used to have those things when I was working with Go. So come on, how can Rust not help me? So in Go, this is how it works. You just include this library, and then it serves the endpoints to trace to give CPU profiles and other things. There is built-in tooling that can download those dumps, and then it can render. Well, this is a flame graph upside down. Don't ask. I don't know. They just decided this is the right order, right? This is the right order. So the nice beauty of this tool set, though, is there's not only flame graphs. There's a few different renderings. So this thing here that is like a full call graph, where you can see who calls who, how often gets called for, how much of the percentage of the running time each of the functions gets. Sometimes this is more readable than the flame graph. Sometimes the opposite. You have to pick your poison. So in this case, as you can see, 65% is in the slow, 34% is in the quick. And all of them call the same factorial, which is the one that where the bulk of the time is spent. So nice, this seems useful. Also, there is like a source level visualization. You can actually see each line of code, how often is executed and for how much of time is spent. So this is cool. So I would really, and this is not just for Go, by the way. So this is Jprof suite is just a dump of Google's internal profiling suite, which is rewritten in Go, and now it's available for the public. You can, so there is a standard profiling format, and there's a bunch of tools which can work with that. You can have that working with C++, Go, I don't know what else. You can even convert the perf data that we showed before into this new format so that you can use this visualization tooling. However, what about Rust? There is a solution. There's this great crate made by this in TICV. I don't know if that's the right pronunciation of this project. They made this great crate called Jprof, which it does exactly what this Go built-in thing does. You just add a dependency to it. You mark where you want to start to profiling with this kind of right guard. And then when they're done, you dump the flame graph into a file or into some byte stream. And you get this, which is similar, a little bit different though. They decided to have it per thread. So in this case, I can have this duplicated thing, but I can easily zoom in. There are a few differences. For example, alongside of the actual function that gets executed, our factorial thing, you can see this backtrace and unwind and this calls here, which are probably what the unknown symbols from perf were. Basically, the machinery that was this computing stack traces during samples also has to use some CPU time to run. And in this case, this sampling being done within the process itself, it knows about its own symbol, while Jprof probably injects some, or perf probably injects some code to do that, which is just not used to symbolize. Cool. So, and the nice thing is that we can also do that on a living running process or the network. So this is what we did in IOx. We just added a little bit of code to expose this dump over HTTP. So if you have access to your debug port, in this case, we are running that on Kubernetes in our staging environments. We have a port forward to the internal port, and now you can just open that thing in a browser. No external tooling. Just open that one in the browser, and we render the flame graph. So we can immediately know what an IOx particular role is doing. In this case, it's parsing a lot of line protocol. You can spot in this thing InfluxDB line protocol something functions. So this is useful, and you can also point to this very same URL. You can point to the Go Jprof tooling, even if the backend is not Go, it's Rust, right? So it just speaks the same protocol. So this renders the flame graph from the Goprof tool, which is analogous to the other one, just upside down. So this is nice because this is like an interactive application that you can render flame graphs, you can render call graphs from the same browser window. You can get like the top functions, the most call functions, and all this kind of stuff. By the way, the same format, this is a standard format. So there are external applications that can also render the very same data. So for example, Speedscope app is just a client-side thing for your browser. You can run your own, or you can use this kind of public thing, but it's not running on a server. It's just running in your browser, right? So you can just upload this basic protobuf file to your browser, and this can navigate a little bit better because you can zoom and pan around and do this kind of stuff. So, and this is how it works, right? So you just have an HTTP handler. You kind of grab the profile, wait for a few seconds until that's done, and then we decided to just detect if it's run directly in the browser, like text HTML or SVG XML header. And in that case, we just render the SVG directly, so that you just render a flame graph. Or if it's run by curl or something like that, we dump the protobuf, which will then be rendered by this other tool, including Go tool Jprof. Okay. So this is an example of the protobuf being decoded into JSON. You can see that this is just a bunch of samples. Each sample says this happened, and this is the backtrace, a bunch of function names, and a bunch of things, and as the SVG if you have the right headers. So this is nice. However, there is one of the frustrating things for me, which I didn't really solve yet, and probably is unsolved in general, is that those stack traces, if I look at the call graph and if I look at the flame graph and so on, sometimes the very same function, it belongs to radically different ancestries because of async. So we use Tokyo async, and so stuff just happen in completely different threads just because there isn't a sync yield point in the middle. So it would be great if Rust had support for async aware backtraces, where you really know who called the async function, and within this very same async function, you know that this line actually happened before the other one, which is right now, in what I showed you before, this is not what you see. You see different kind of independent lineages because the sampling only looks at the physical backtrace, not the async aware backtrace. It's like an open question. Okay, this is for heap for CPU profiling. For heap profiling, okay, so I started doing the obvious, which was let's use a memory allocator that knows how to do heap profiles. And so there are a bunch of them. We use JMalloc for other reasons as well, but JMalloc is one that that can dump the heap dumps, and you can analyze them and so on. So one trick is to use JMalloc for your Rust application, is to use this JMallocator crate, install it as your global allocator. And so all the Rust code will, when Rust code will lock, it will go through JMalloc. There is also a possibility to kind of replace the system malloc, so that also your C libraries go through the JMalloc, or whatever you want. So once you have your binary running on JMalloc, you can pass some environmental variables to cause a heap dump every at the end of the program, or every, I don't know, few megabytes of allocated memory. And then there is a tooling called Jprof, Jprof, which does this kind of call graph thing. I didn't figure out how to symbolize those addresses. I try to like run the symbolized thing. Those addresses just, I don't know, they don't match to anything. So there might be a way to have that, but it's not only this. I would like to have a flame graph out of that. I would like to have the very same visualization, goodies that the CPU profiling that we just saw had. So I don't know, perhaps I can figure out how to massage this Jprof into that format. Perhaps that's a way, or there's another way. My second attempt was to just literally hook into calls to malloc so that it would work with an allocator. It would work with JMalloc, it would work with system malloc, it would work with anything else. It will intercept calls made by Rust, and it will intercept calls made by your C dependencies. So for example, a lot of memory allocations in IOx are actually accounted to the C roaring bitmaps library, which we have this Rust binding to the C library. So I really wanted to not gonna be blind to that. So one interesting trick line, like getting a little bit more low level into the Rust C foreign function call tricks. So this is basically two parts of it. So I have to intercept malloc. So malloc, the system malloc in libc and so on, is a weak symbol. So that means that if your binary implements the same function that is called with the same name, it will override the one that is provided by libc. So far, so good. You can basically run your own code. But I want to call the system allocator again, right? So it turns out that you could do that with the linker flag called --wrap, but it's very hard to have that working in a cargo. To pass a specific flag to the link to the last linker step. You could do that manually, but it's very hard. So I just thought, you know what, we're going to use JMalloc anyway, So let's just call JMalloc instead of calling the libc malloc instead. So this is every Rust code and every C dependency will call malloc and free and calloc and whatnot. It will be intercepted by this little function here, and that function will track memory allocation stats and traces, and then it will call the other one. It will perform a foreign function call to a C library called air JMalloc, which is the symbol in the JMalloc library. So far, so good. So there are a few of them you have to intercept though. So it's not just about malloc. There is other variation on the theme of malloc, including Realic and so on, which some of them are like, basically tricky, because if you're realocking, you know the final size, but you don't know the old size. You have to figure out the current size of the object before, and then compute the delta, and so on. But it's doable. So the second problem was, once you implement the function to track memory allocation, well, in order to track that, you probably have to do some allocations in turn, right? So simple stupid way I've found is to use a kind of thread local, a Boolean, and make sure to prevent reentrant execution of this function by using this in thread local. Probably there are better, nicer ways, but I'm just learning Rust. So basically, I'm sampling. So if you have a very precise recording of all the memory allocations, that's okay, acceptable when the software is not really doing many of them, or when you're just running a test on your laptop. But if you want to have like a minimally disrupting thing on a running process, you should just do sampling, statistical sampling. So what we do here is that we have like a rate parameter that says every megabyte or so, every time that the current memory allocation crosses this kind of sampling period, we will sample that thing. We'll compute the stack trace for that allocation event, and then over time we'll probably observe more frequently some of them than others, but we will capture how much memory each of them will consume. So this is the result of that. I've run this into a small synthetic example where I knew exactly how much memory I was allocating, so I could actually check that. Oh, sorry, the screenshot doesn't show the actual amounts, but there are. If you hover on this profile, you can see how much memory was called by this foo new function, how much memory was called by this other thing, and so on. And the very same data that it was used to render that flame graph is also used to render this this call graph, which has nice numbers. It says like 3 megabytes went through this, and so on. And yeah, that's mostly it. Do you have any questions?
Fantastic, Marco. It doesn't look like there's any questions right now, but what can the community do, as you guys are continuing to work on this, what can the community do to help or, get more involved in IOx?
Well, in this case, this is a general problem. So this is not a IOx specific problem. So if anybody in the community would like to help in better observability tooling for Rust, it's in particular heap profiler, which there is a little bit of work around, but it's not, I don't know, I didn't see that much being done there. So that can definitely be something that is widely useful for everybody. For in particular, being in memory database, having a good heap profiler will definitely help us with some headaches. Sometime. But yeah, in this case, there's nothing really IOx specific.
Okay.
I would say on the, I would just chime in really quick on the IOx front. Right now, contributing to IOx itself would be pretty difficult because we have a lot of stuff still moving around and we're still, getting everything kind of gelled together with all the new team members that we've added recently. But one thing I will say is recently, the Rust bits of Arrow were pulled out into a few separate repos. So there's the Rust Arrow repo, which is under GitHub, Apache, and it's arrow-rs. But actually the more interesting one is the Data Fusion repo, which I believe is arrow-data fusion. And that, so the Data Fusion repo is actually essentially the query engine that we use within IOx and we're actively contributing to. And that has a number of issues that are basically just like new bits of query functionality, essentially like implementing functions that exist in Postgres that don't exist in Data Fusion and some other stuff. So that is likely going to be the most accessible way to add to IOx, but really you're adding to the Apache Arrow Rust ecosystem. And yeah, Andrew, did you have more on that?
Yeah, I think it's a cool, if you're at all interested in query engines or how SQL works or whatever, there's lots of like little things you could work on in Data Fusion that would teach you that, plus add features for both IOx and other projects. So I think it's a good suggestion.
Oh, now I'm sure you guys are all tired of getting this question. I just saw it again today in the Slack. Do you guys have any sort of timeline for releasing something?
So here, one second. I actually just responded to this one while the talk was going on. So the question was, when is 1.0 going to be out? And to that, I would say, I don't know. A lot of things have to happen before 1.0 happens. So for example, with the original InfluxDB, first public code release was in November of 2013. 1.0 didn't happen until September of 2016. Obviously, there was a lot of code and builds and documentation, stuff that you could use along the way. So our intention is to run IOx in production in our own cloud environment as initially as a service that people can opt into as part of the cloud environment as an alpha build, and then later something more aggressively production worthy. So we're going to do that first before we actually start producing open source builds with documentation and stuff like that, mainly because we want to make sure that when we do produce open source builds and documentation, it's something that's worth people's time to test and stuff. If you're a Rust enthusiast or a database enthusiast and you want to get involved earlier, that's great. And we have, a bunch of stuff in the repo and we have, the community Slack and stuff like that. So we welcome that kind of contribution. But that release, in our cloud product is going to be later this year. And after that, we will be producing official builds with documentation. Those won't be 1.0 builds. They'll be, something earlier than that, because we need to give the community time to play with things before we finalize the API and everything to say it's 1.0. So my expectation is that we will be producing those builds and that documentation, later this year. But as far as timeline goes, there's still a lot of moving parts. So we still have a lot of stuff we're doing. But with that being said, things are moving ahead pretty quickly. In our own environment, we have multiple IOx servers running that are ingesting data. I think one of them is ingesting somewhere on the order of 58 megabytes a second of line protocol and buffering that in memory and buffering it into our, read buffer, compressed in-memory data store, and then also putting that out into Parquet files in object store. So we're spending time optimizing that kind of life cycle, and building the recovery components of it, which is the database catalog and all these other pieces. So things are moving, but still too many unknowns to commit to a specific timeline.
Well, it's definitely exciting seeing how big the IOx team has gotten in just the last few months. So I'm sure you guys are super busy. Let's see, there is a question here. Will there be any profiling of queries? Can we see top 10 queries that are causing high CPU or mem?
So one part of the checking query stuff is the explain plan functionality, which thankfully actually exists. And I believe that's getting better literally by the week. But then the other part is obviously profiling active queries in the system. So there will be a way to see what queries are running. But the truth is, if you want to profile queries after the fact or whatever, we have to build a bunch of observability tooling around the production IOx servers that we run. So those will be outputting metrics and tracing data, which we will be ingesting in separate servers to be able to do that kind of checking. So how much is going to be in the IOx process itself versus how much we kind of offload to an external tracing system is, I think, TBD. We still don't know yet. But the idea of building, making sure that things are very observable and you can see what's going on in the server, where things are slowing down, and all that kind of stuff is obviously very, very important to us. That's one of the reasons why Marco has, given this talk today about profiling, is because he's done all of this kind of work in an effort to get visibility into what's going on in our own, pre-production setup that we're running, where we're mirroring a production workload into IOx.
All right, well, we'll just stick around for a little bit, see if anyone else has any other questions. Paul, is there anything else that or anyone else part of the team wants to share of what they're working on, or any update? The joys of having these every month, right?
Yeah, I don't think there's anything on our end. There are a few documents that we've put into the repo that might be of interest. If you look at, just in the repo, if you look at the docs folder, basically some of the design documents that we've done along the way have been pulled out into markdown files in that folder. So some of those are interesting, and you can basically look at the Git commit history to see when those were added. Some of it is a bit dated. Things that are added most recently are obviously most relevant. I think the catalog design is probably the most recent interesting bit. And then there will be a new document going in probably next week, detailing like the data lifecycle design. So.
Oh, yeah, and we have these IOx Tech Talk sessions every month. So, the team is always working on new stuff and figuring out what the coolest thing is to show you guys. So I'm just going to throw in the Zoom chat, the registration link for next month. So we have these on the second Wednesday of every month. So we definitely like to see you all back again. It's always fun to see familiar names popping up in the attendee list. Once again, we do have Influx Days North America 2021 coming up. Of course, it is going to be virtual again this year. I think we're all really excited to get to see each other in person, but it's still fun getting to hang out virtually. This for the May event, it was really cool. We had office hours with the IOx team. We had a trivia and happy hour. We also had Grafana office hours. So really excited to see what we do for the fall event. We're always working on improving it and making it more fun for our community. So hope to see you all there. Hope to see you at the next month's IOx Tech Talks. If there aren't any more questions from the audience, I think we will end things early today. Cool. Well, thank you everyone for joining, and thank you to the IOx team for coming on, and thank you, Marco, for presenting.